hi again, folks. I hope you found something nice and fun to do today other than schoolwork, but that playtime is over because now it's time to do some chemistry. Sorry about that. Well, we're going to talk about thermodynamics, or at least those aspects of it that lend itself to chemistry because that's kind of what we do. And I'm sorry I can't be delivering this in person. I'd much prefer to be standing in front of y'all, but we'll do our best. Now, the three laws of thermodynamics start off with number one being the law of conservation of energy, or matter and energy. And in essence, it just says that energy can't be created or destroyed. It can be changed from one form to another. Sometimes you see it written that the total amount of energy and matter in the universe is fixed, meaning that nothing gets in, nothing gets out, which I'll assume is true since I've never been to the edge. But in order to understand this conservation of energy, we need to define something, a state function. A state function is a property of matter that depends on what state it's in, meaning if its temperature would change or its pressure would change, that state function might change. Well, the first thing we need to define is something called the internal energy of a system. Well, the internal energy of a system is the sum of all the energy that's in there, the potential energy to do something and the kinetic energy, the things that are in there moving around. If it's above absolute zero, you know it's vibrating, the molecules are. So even if I just had a peanut has some potential energy. It's got a certain number of calories in there that I know if I ingest it, I can use that energy. And so there's potential there. And inside the peanut, there's carbon atoms with electrons whizzing around the nucleus. And so there's kinetic energy in there. So if I summed all that together right down to the last little electron, that would be an indication of what's called its internal energy. Now, whenever any kind of a process occurs then, whether it's a spontaneous process or whether it's a process that you have to push it uphill, there's going to be a change in this internal energy. So this change in U, a change in internal energy, always manifests itself as two components. It'll either manifest itself as heat, or it may manifest itself as work. All right, we discussed this way back in chapter 6 in Chem 130. But just to go back over some old ground here and maybe fill in a few gaps, we might expand on it a little bit. We had a sign convention. So again, anytime there's a process, whether spontaneous or not, it had an internal energy at the beginning and it had an internal energy at the end. Very likely those two numbers are not the same. So in any kind of a process, there's going to be some change in U, so that's a delta U. And again, that change in energy is going to manifest itself as either heat or work. Now we recall that we always assign a negative value to the Q, the amount of heat involved in a process, if it's an exothermic process, meaning that heat is evolved. The more general symbol for heat is Q. If it's given per mole of a substance, they usually change that to a delta H, which stands for the enthalpy of a reaction. I'll explain that here in a little bit. Now, if the Q value is assigned a positive value for endothermic reactions, all right, well, this is something that we've discussed in the past. This is where heat is absorbed. Now, endothermic reactions get cold to the touch, and it's because that heat gets absorbed, but it's actually converted into different currency. It's converted into new bonds, and so the heat actually vanishes and is transformed into another form of potential energy. And so in an endothermic reaction where heat's going into the system, it actually gets very cold to the touch. Exothermic reactions get very hot to the touch. Now we have kind of the same sign convention when we talk about the work that's done by a system. And we'll discuss work here in a little bit more detail. But work is assigned, and they use the symbol W for work. Work is assigned a negative value if the system does work on the surroundings. Now, most books spend a lot of time discussing the difference between what they call the system and the surroundings. Very simple. When we do a reaction in a beaker, everything that's inside that beaker, that's the system. Everything that's outside that beaker, that's the surroundings. Pretty simple. All right, so if the system does work on the surroundings, then we assign that a negative value, meaning that it's expending itself. On the other hand, it's assigned a positive value, sort of endothermic, if the surroundings do work on the system. All right, well, that begs the question, what kind of work are we talking about? I mean, it's not like I dump a bunch of chemicals in a beaker and they're going to jump out of there and go do the dishes for me. So what are we actually talking about here? Well, it turns out that from a chemistry standpoint, there are ways to get work out of a chemical reaction. For instance, a battery chemical reaction. It's a flow of electrons. We can push electrons around and sure enough measure how much work that system can do. But just to keep things simple, let's look at the idea of expansion work. Due to the formation of gases. Because this is an easy reaction to discuss, and it's easy to show exactly how much work you can get out of a system when it's expanding. For instance, when the gasoline burns in your car and it creates carbon dioxide and water as a vapor, well, suddenly there's more moles of gas, and as it expands, it pushes the piston down, it turns the crankshaft, moves the car. All right, so there's clearly some expansion work going on there. Well, let's look at a particular reaction. Suppose we looked at the reaction of magnesium, a couple hydrochloric acids, to make magnesium chloride and hydrogen gas. And suppose we reacted 1 mole of magnesium, so we got 1 mole of hydrogen gas produced. And we did it in a beaker fitted with a piston. Let me draw a little piston in here. And we'll put a little weight on top of it. So now the hydrogen gas is being produced down here in the reaction. We dumped a bunch of magnesium and hydrochloric acid down here, and it's pushing the piston up inside the cylinder, inside the beaker. Well, essentially then it's doing some work, because work is force times distance. So if it moves this piston a certain distance, then it's definitely doing a certain number of joules of work. Well, what's interesting is we can calculate that amount of work for 1 mole of gas being produced by using the ideal gas equation. As a matter of fact, they generally talk about expansion work in physics and call it P delta V work. Okay, I just wanted to insert this to talk a little bit about this idea of work. Now, work is defined in physics as force times distance, meaning a certain amount of force applied to an object over a distance can be measured as a certain number of joules of work. But when you're looking at the expansion of gases, the force that is actually being exerted is the pressure of the gas. And the distance would be the change in volume of the gas. For instance, if the gas was pushing a piston out of the way, that distance could be measured, but essentially that's because of a change in volume. So often physicists refer to work as pressure volume work, P delta V work. All right, back to our show. Now I should say that there's going to be a negative sign in front of this, because if the system is doing work on the surroundings by producing that gas, then it, by sign convention, is assigned a negative value. Now, essentially then, the piston is pushing against the pressure that's in the room. And so that's, we'll assume, is not changing. However, the volume of gas that's being produced is changing, because 1 mole of gas from nothing, suddenly there's some liters of hydrogen gas. Well, P delta V would essentially be equal to delta N times RT. Note the ideal gas equation, PV equals nRT. This change in volume is due to this change in the number of moles. Well, if I put in 1 mole for the change in the number of moles of gas, meaning there were no gases on this side, and suddenly I have 1 mole of gas on that side. Well, negative 1 mole, the R constant, let's go back to chapter 15 and grab that R constant that was in kilojoules. It was 0.008314 kilojoules per mole K. And let's do this at 298 K. 25 degrees centigrade. That's generally what they like to use for standard thermodynamic measurements. Well, this turns out to be negative 2.48 kilojoules per mole of gas produced. Now, that's kind of an interesting constant, because that means any gas that gets produced is going to try to expand into the system. And in the process, even if the piston is not there to push out of the way, it's pushing other gas molecules out of the way. So it's still doing that expansion work, whether or not we harness that work or not. And it turns out for each mole of gas produced, you actually get almost 2.5 kilojoules worth of work at 25 degrees centigrade. Let me just show you a way to apply that. We were talking about gasoline. Gasoline, let's suppose you're running pure octane in your gas tank. That's C8H18. Well, it reacts with oxygens to make CO2 and water. And it produces them both as a gas because it's hot. It's going to produce both of them as a vapor. The oxygen's a gas. Your fuel injection system vaporizes this, so it goes in as a gas. Now, if we balance this, it's going to take 2 of the octanes to do the trick, and that's going to give us 16 CO2s and 18 waters. And in doing that, I think we're going to need 25 oxygens to make this balance. So you'll notice something here about the combustion of 1 mole of octane goes from 27 moles of gas on this side of the equation to 34 moles of gas on this side of the equation. There's a change in 7 moles of gas from reactants to products. Well, then technically, if we were to run this reaction, and it wouldn't run at 25 degrees centigrade, it would very likely get a little hotter, and so there's heat given off by this reaction. But in addition, there's mechanical work that can be harnessed by that 7 moles of gas that's produced. As a matter of fact, it's this amount per mole. Now, I don't know why the book doesn't stress this 2.48. It's just kind of a handy little constant. You can understand if you're an automotive engineer, that's a constant that they use to look at the mechanical side of the expansion work done by the combustion of gasoline. All right, well, let me show you how this applies also to our change in U. Okay, so given what we just talked about, suppose you had an exothermic reaction that gives off 100 joules of heat. All right, so the Q value would be negative 100 kilojoules. Well, suppose it also produces 7 moles of gas at 1 atmosphere and 25 degrees centigrade. Well, and I want to know, what's the change in U, the delta U for this process? Well, again, since delta U is Q plus W, this would be the negative 100 kilojoules for the heat that was given off, plus 7 times 2.48 kilojoules for the gas that was produced. Remember I said that each mole of gas that's produced gives off that 2.48 kilojoules. Now again, that's a negative value. So this ends up being minus 100 kilojoules for the heat. Am I going out of range here? No. And what does this come out to be? 7 times 2.48 came out to be 17.4. Negative 17.4 kilojoules. All right, well, minus 100 plus another minus 17.4 is minus 117.4 kilojoules. So again, there's a couple questions like this at the beginning of the homework that I assigned where they're just checking to see if you remember that sign convention. The idea that if it's exothermic, then there has to be a negative sign in front of the heat. And if the system is doing work on its surroundings by producing a gas, or they may just paint some other scenario and tell you how much work the system does, then you just got to remember that that also has a negative sign in front of it. Okay, well, let's move on to the next topic. Okay, well, this little trip down memory lane about delta U, the change in internal energy, something we discussed back in Chem 130, was really only so that we could bring ourselves back to the threshold of discussing delta H, the enthalpy of a reaction. Now, this chapter basically hovers around reaction spontaneity. What drives a reaction forward? And one of the major players in that is the enthalpy of the reaction. Exothermic reactions are very favored. They're rolling down the heat hill, as opposed to endothermic reactions, which are rolling up the heat hill. And so consequently, measuring delta H's was something that we looked at back in chapter 6, and we need to sort of revisit here. So here's a discussion on our different ways of how we measure delta H. Okay, well, back in Chem 130, we introduced the idea of the heat of a reaction, but back then we called it the enthalpy of the reaction, delta H. We didn't really go into too much detail there, but let me expand on it a little bit. It turns out that the enthalpy, the heat of a reaction, is the heat produced by a reaction at constant pressure. That means that you don't let pressures build up. Like, for instance, if gases are produced, you don't put a lid on it. You leave it open to the outside atmosphere so that the pressure doesn't change. All right, well, that's referred to as the heat of the reaction. Now, there's a subtle difference between the heat of a reaction at constant pressure and the heat of a reaction at constant volume. And so let me just quickly show you the difference, and then we'll get back to this discussion of enthalpy. As a matter of fact, let's look at that same reaction of magnesium. As a matter of fact, I think we may have talked about this back in Chem 130. I may have gone this far. If we ran the reaction of magnesium and hydrochloric acid to make magnesium chloride and hydrogen gas, it turns out it's pretty exothermic. It'll give off some heat. As a matter of fact, I'm going to have you guys do a lab that involves this reaction and have you measure the heat with a calorimeter, one of those real expensive styrofoam cup calorimeters. Well, if we ran this reaction in here, and suppose in the first vessel, we just let the hydrogen escape. So no lid. Well, it turns out that this does give off some heat. Because if you held the beaker, it's going to definitely be warm. But the work that's being done is not being harnessed. We're just wasting the work on the surroundings. All right, just letting the hydrogen just push gas molecules out of the way. So we're doing this at constant pressure. So that means this is the heat at constant pressure. On the other hand, if we put a lid on this, cap it, and run the same reaction, and now the hydrogen gas pressure is building up in here. Well, if I put both of those beakers in your hand and I ask you, well, which one do you think would get a little hotter? Instinctively, you're thinking this one, and that's exactly right. And here's why. The work is trapped. It can't push a piston, it can't do anything, but suddenly the pressure builds up in there. That energy, that work energy, has to go somewhere. And it manifests itself as additional heat. So the heat that's coming out and the work that's coming out, essentially what you're feeling on the bottom of that beaker is all of delta U. You're getting the work component and the heat component. This heat is called the heat at constant volume, Q sub V. So Q sub V is essentially what delta U is. It's all of the work and all of the heat just lumped into one because we didn't let the work manifest itself. We trapped it. On the other hand, Q sub P is called the enthalpy of a reaction, delta H. All right, so subtle but significant difference here. If we send you into the lab, it's very unlikely we would let you measure a delta U for a reaction. We could do it, but you can see the danger there of putting a lid on something and letting the pressure build up and see if something bad would happen. It might. So generally when we go in the lab, we run reactions in open vessels. So the heat that we're actually measuring there is always the heat at constant pressure and always referred to as the enthalpy. All right, well, let's see if we can tie this all together. Okay, so just to refresh your memory on what we talked about, I got chalk dust on me. Just what we talked about delta H back in Chem 130. In measuring the heats of reactions in open vessels, again, so no pressure builds up, we did them in styrofoam cups. And calorimetry is what that's called, is when you measure the heat absorbed by the surroundings. So the heat given off by the reaction inside the cup was equal to the negative of the heat absorbed by the surroundings. I'm going to send you a Hess's Law lab that I just currently am doing with the Chem 130 group that I'd like you all to work through because it refreshes your memory on specific heat and heat capacity, and it explains that whole thing. So anyway, I'm going to send that as soon as you've seen this lecture. I'll give you a lab experiment to do that's, again, on Hess's Law. I'm sorry, not Hess's Law, but on calorimetry. Now, in addition to experimentally measuring the heat of a reaction, again with styrofoam cups and temperature probes, we also looked at something called the summation of heats of formation back in Chapter 6. So let me get rid of this. Okay, well, back in the day, we played this game about the heats of formation, the sum of heats of formation. And the heat of formation of a compound was defined as the energy required to produce a compound in its standard state, meaning 25 degrees centigrade, 1 atmosphere pressure, from its component elements, likewise in their standard state. So, in essence, what they said was, let's assign a value of 0 for just the elements. All of the elements in their standard state, the delta H of formation is 0. Meaning that that's sort of like sea level. Anything that requires you to put energy in goes above sea level. Anything that you put the elements together and it goes below sea level is more stable than the elements. So they just arbitrarily chose the elements to be sort of the reference point from which we're going to measure all energy changes. All right, well, the appendix in your book has a list of all the compounds that you'll ever need and their standard heats of formation. Well, the game was actually just an arithmetic game. It just said that if we summed up all the heats of formation that are locked inside our products in a reaction, and then subtracted from that all the heats of formation in the reactants, the pile of energy that we began with compared to the pile that we ended with, that difference would be the delta H of the reaction, theoretically, and sure enough, experiment bears that out. So the heat of a reaction then is equal to the sum of all the heats of formation of the products minus the sum of all the heats of formation of the reactants. All right, well, just to show you a quick example, suppose we looked at the combustion of methane, CH4 as a gas, oxygen as a gas, going to CO2 as a gas, and 2 waters as a liquid. Well, it turns out that the heat of formation is minus 74.9 kilojoules per mole for methane. If you look it up in the appendix, that's what you'll find. Oxygen has a value of 0, again because it's a pure element in its elemental state, in its standard state. CO2 has a heat of formation of minus 393.5 kilojoules per mole. The more negative these are is an indication of how stable the compound is. So it's definitely more stable than the methane, and this is why we're going to get a net exothermic reaction. The water is a liquid, minus 286 kilojoules per mole, but there's 2 moles. So we're going to have to multiply that value by 2. Well, the delta H for this reaction then would be the sum of all of the products minus the sum of the reactants that's here. And so the delta H, let me go ahead and put the numbers up here. This delta H would be the minus 393.5 for the carbon dioxide, plus 2 times minus 286 for the two waters. Then we're going to subtract from that, let me go ahead and put the parentheses there. We're going to subtract from that the minus 74.9 for the methane and the 0 for the oxygen. And I think I didn't even balance this. We needed 2 oxygens. So let me make that 2 times 0 up there at the top. Well, let me grab my calculator here. I think I've misplaced it. Oh. So 393.5. Somebody back me up out there. Let's see. 6. 74.9 subtract negative 74.9. I got negative 890.6. So apparently the combustion of methane must be exothermic to the tune of 890 kilojoules. Now again, it's an arithmetic problem. All you have to do is look up the standard heats of formation for all your products, subtract all your reactants. Hopefully this looks familiar. All right, there was one last method that we used for calculating delta H. And let me get rid of this and we'll look at it. Okay, well, Hess's law was where we added and subtracted, or actually added whole reactions to one another. Cancel out anything that was the same on both sides of the arrow. But there were some rules about Hess's law that we would give you pieces to assemble a reaction, but sometimes you had to flip the pieces over, maybe reverse the reaction to get the species that you need on the proper side of the arrow. Well, in that case, we changed the sign of delta H. If we took any multiple of the reaction, we had to take the same multiple of delta H. And then once we summed them together, we summed up all our manipulated delta H's to get the theoretical delta H for the reaction. Again, the Hess's law experiment that I'm going to send you illustrates a couple examples of that. So anyway, there's 3 methods then for looking at measuring the delta H. One experimental, just calorimetry, go in the lab, run the reaction, measure the heat given off by it. Or 2 theoretical ways. You could just go to the standard heats of formation and sum up the products, subtract the reactants. Or Hess's law. If you've got several reactions whose heat you already know, and the sum of those reactions equals a reaction of interest to you, you can calculate theoretically the delta H of that reaction. Okay, so those are the 3 ways to look at the heat. And this is, again, just a recap of something we looked at in the past. Okay, reaction spontaneity. This is what this chapter really is all about. Will a reaction just take off all by itself, or are you going to have to push it and push it and push it to make it go? Now, there's a lot of reactions that are spontaneous, but it doesn't necessarily mean they're fast. For instance, coal being converted into diamonds is a spontaneous reaction, but it takes a little bit of time. So the idea of reaction spontaneity, when you look at the heat of a reaction, for instance, an exothermic reaction is essentially rolling downhill. You've got your reactants up high in terms of energy and your products down low. And that seems like something exothermic, like setting a log on fire in your fireplace. Even though you have to provide a little energy of activation, a little match to get it going, it's definitely exothermic and it's definitely spontaneous. It'll propagate itself. And so exothermic reactions, it seems like, well, those should be spontaneous. Since it's sort of rolling downhill, it's going to a much more relaxed place from a much more tense place. All right, and so an endothermic reaction, you would think, well, not likely to happen spontaneously. When your reactants are low in energy and your products are high, energy is going to have to be absorbed from the surroundings for that to happen. But it turns out that enthalpy is not the only driving force behind a reaction, because there are endothermic reactions that go spontaneously. For instance, those ice packs that you can buy at CVS, you crunch the little capsule inside and suddenly the thing is frosty. Well, that's an endothermic reaction running spontaneously inside that bag. So clearly there's something else here driving this reaction to push it up the heat hill. Well, it turns out that other driving force is entropy. And so this is where the second law of thermodynamics comes in. All right, so let's start second law. Okay, so entropy, the other driving force behind chemical reactions. And this is a good one because it's really technically defined as the number of energetically equivalent ways to arrange a system. What it is a measure of randomness. It turns out the driving force behind a lot of reactions is their ability to create randomness. All right, well, and a matter of fact, let's get the sign convention right here. Positive delta S means things are more random. If it's a negative delta S, that means they're getting more orderly. Now, things don't usually spontaneously become more orderly. They usually spontaneously become more random. Look at my office. I can go and shut the door, leave for a couple weeks, come back. Somehow it's more random than when I left it. Well, that's the second law of thermodynamics at work on my office. But again, the idea of randomness is really kind of wispy. I mean, how do you actually measure the randomness of a system? Well, they actually have a mathematical formula for how they define the total number of different ways you could arrange a system. For instance, just with a deck of cards, it's easy to show how randomness gets worked into a system. If I were to set one card down here, there are 52 possibilities of what that card is. But if I said, no, I'm going to set 2 cards down instead of just one, how many possible ways now are there for those 2 cards to come out? Well, there's 52 for this one and 52 for this one, so it's 52 squared would be the number of possible arrangements of those 2 cards. So suddenly the number of possibilities went up, and that increases the randomness of the system. Now, it depends. I mean, it turns out that the universe likes this randomness. As a matter of fact, the second law of thermodynamics says for any spontaneous process, the change in entropy for the system and its surroundings is always positive. There's going to be an increase in the entropy of the universe when anything happens. So that means ultimately the universe is going to reach infinite randomness. Now that phrase alone just kind of blows me out of the water, because here's the idea. If I were to give you a deck of cards and send you into a room and say, okay, arrange them randomly on the floor. So you take the cards and you throw them all over the floor. And we're all standing out in the hallway and we're looking at the room. We're thinking, yeah, that's pretty messy. You know, you got them in there pretty random. Could you go in there and make them a little more random? So you go in and you kick them around on the floor and you just pick up a few of them, throw them in the corners, throw them everywhere. And so, yeah, that looks more random than it looked before. But could you go in there to make them infinitely random? Well, if you go in the room with a plan to make them infinitely random, you have a plan. Suddenly, the randomness went out the window. So the idea of infinite randomness almost implies that there's some kind of order involved there. I know that, just it makes my eyeballs hurt thinking about it. But the concept here is that ultimately, all the available energy in the universe will get consumed. And you reach what the thermodynamicists like to call a heat death, where nothing else can happen at that point. So hopefully that's billions and hundreds of trillions of years away. All right, so randomness. It turns out that this is the driving force behind a lot of reactions. That little ice pack that I mentioned before, when you crunch that capsule in there, that ammonium nitrate capsule that's in there, actually as it dissolves, becomes completely randomized out into a solution inside that bag. So it turns out that there's not only a heat hill, exothermic running down the heat hill, but endothermic running up. There's a randomness hill. The randomness hill runs down when things get more random. It likes that. The universe loves that. It runs up the randomness hill when things get more orderly. And again, the universe doesn't like that. So with those 2 hills in mind, you can understand then if they're competing with one another. What if there's an endothermic reaction that's going up the heat hill, but it's creating so much randomness going down the randomness hill, enough to pay for this little bit of heat that's being absorbed by the system. So in essence then, you'll get a spontaneous endothermic reaction, like that ice pack. So the randomness hill, the heat hill, we need to look at the difference between those two to decide whether overall the reaction is still running downhill or running uphill. All right, well, let's throw some numbers on the board. Okay, generally in our discussion of randomness, of entropy, we point out the fact that orderliness can be created. I mean, the blocks in the wall in our building are nice and neat and orderly. But for that orderliness to be created, The second law of thermodynamics says a greater amount of disorder was created somewhere else. The trucks that drove the bricks here, they randomized gasoline molecules. There was a lot of disorder created in order to make those blocks, to bring the blocks here, even down to the Egg McMuffin that the worker ate that morning, that he randomized into a bunch of different molecules. That counts. That's entropy that was created to create this orderliness. But ultimately, the net change is that the universe just got a little bit more random. So all processes, according to the second law of thermodynamics, create some increase in entropy in the universe. Okay, well, the second law of thermodynamics, which is what this chapter is all about, says that the entropy of the universe, and what I mean by the universe is the system and its surroundings. It's the whole shoot and match. Somewhere along the line, entropy is going to increase for any kind of a spontaneous process. All right, so that just says again that the universe is going to eventually reach that ultimate entropy. And so the standard free entropies that they list for you in the appendix of your text, or sometimes called the absolute entropies for compounds, are given in the units of joules per K. And that's kind of interesting the way the units are derived, because entropy essentially goes where the heat goes. When heat enters a system, it gives more energetically equivalent possibilities and increases the entropy of the system. And so it's sort of tied to specific heat. As a matter of fact, if we took something at 0 Kelvin, theoretically, and then warmed it up and looked at how many joules it took on the average per degree Kelvin to get it all the way up to standard temperature, 25 degrees. If we looked at that in the number of joules on the average it took to change it 1 degree Kelvin, that would be joules per K. And that's the unit then that they measure the standard entropy. So it was on the average how many joules it takes to change it 1 degree Kelvin, all the way from 0, integrate all the way from 0 up to 298 Kelvin. All right, well, again, the appendix shows, hold on a second, let me find my eraser. The appendix has a list of all the standard free entropies for all these different compounds. So if I wanted to calculate, say, the change in entropy for some kind of a spontaneous process, for example, I've got one here, if we were to look at just water as a solid, going to water as a liquid, well, it's going from a nice crystalline solid state into a much more random liquid state. Well, it turns out that the entropy increases. As a matter of fact, if we look up the standard entropy for water as a solid, it's 41 joules per K. On the other hand, if we look at water as a liquid, it's got a standard entropy of 63 joules per K. All right, so you can understand that as things become more random, their entropy increases. Well, if I wanted to know the change in entropy, essentially then I take the products minus the reactants, so it's a summation law again. You just take the standard free entropies of the products minus the standard free entropies of the reactants. In this case, we take 63 minus the 41. Well, that equals a 22 joule per K change in the entropy when water goes from solid to liquid. All right, so the summation law, again, is just an arithmetic problem. Remember that if you use 2 moles here, I should say that this is joules per mole K, because, again, if there's more than 1 mole, you have to multiply by the coefficient, just like we did with the standard enthalpies of formation. All right, well, let's take a little bit closer look then into the second law of thermodynamics and how to predict, in general, when the change in entropy is going to be a positive value. Okay, so a few little generalities here about entropy. Early on in the homework, they show you some reactions, and they just simply ask you, well, do you think this is an increase in randomness or a decrease in randomness? Now, don't get me wrong, there can be spontaneous processes that the system may have a little decrease in the entropy, but the universe is going to, if the heat flows out of the system, then the entropy that's created by that in the universe is going to make a net positive change in the universe's entropy. But the system itself could have a slight decrease in entropy if it were paid for, by the delta H. So here's the thing. When they want you to look at something and just in your mind decide, well, is it getting more random or not? Because we know that randomness is favored. Well, when big molecules break apart into a bunch of small molecules, that's a pretty good indicator that that became a more random system. It's like the cards that I showed you, that, you know, if we had a lot more players there, then there'd be a lot more possibilities. So certainly if big molecules break up into small ones, that would be a positive delta S. On the other hand, if more gases are produced on the product side than on the reactant side, gases are very entropic. I mean, solids are pretty orderly. Liquids are a little less orderly, a little more randomized. But when you make a gas, the entropy really jumps up because gas molecules are really randomized. And there's a lot of different possibilities for their orientation. All right, so remember we called that the delta N sub G way back when we were doing kinetics. That's the change in the number of moles of gaseous product versus gaseous reactant. So if the delta N sub G is a positive, meaning there's more moles of gas on the right than on the left, then that's definitely going to be more entropic on the product side. The last one is a move up in phase. Well, again, I just said solids are less, random than liquids, less random than gases. So if you go from solid up to liquid, you're increasing the entropy, and if you go up to gas, you're introducing a lot more entropy. So if they show you a phase change in the homework, for instance, solid water going to liquid water, you could predict right off the bat, yes, that's going to be a positive change in the entropy of that system. Okay, so for spontaneity then, if we looked at delta S for any kind of a spontaneous process, for instance, if I just set a little bit of gasoline on fire, well, there's going to be some heat given off by that, and there's going to be some entropy just caused by the process itself, the randomization of those larger gasoline molecules into a whole bunch of small carbon dioxide and water molecules. So there's some physical randomness created by the system, but there's also randomness caused by the heat flowing from the system to the surroundings. Well, if that's the case, if the overall change in the entropy of burning that gasoline is really a function of two components, I could say, well, then the delta S has to be greater than the randomness of either of them alone. So for any spontaneous process, then, we could pretty much say that the delta S would have to be at least greater than the Q over T, right? Because if the delta S is actually two components and we eliminate one of them, then the delta S for any spontaneous process would have to be greater than the Q over T. Little chalk test. Okay, so for spontaneity, delta S then had to be greater than Q over T. Remember that the Q's that we're actually measuring for these reactions are generally measured in open vessels. And so this is the heat at constant pressure. Well, if you remember, that's delta H of a reaction. So this simply means there's a relationship between delta S and delta H for spontaneity. Well, I kind of alluded to that a little bit ago about the hills, that it's a trade-off between the entropy hill and the enthalpy hill as to whether the net sum of the two would still be downhill or might be uphill. Well, let's rearrange the equation. If this is now just delta H, then let's multiply the T across and say, well, delta H minus T delta S has to be less than 0 then for spontaneity. What I did was I multiplied the T across and I subtracted this from both sides, and then I kind of flipped it around to put it less than 0. This simply means the difference between the heat hill and the randomness hill has to be a negative number, meaning it still has to be downhill for spontaneity. So this represents the change in the heat, whether the heat goes up or down. This represents the change in entropy, whether it gets more random or less random. And the difference between those two, in order for a reaction to be spontaneous, has to be less than 0. Now we have assigned a name to this value, whatever that value is referred to as the Gibbs free energy. This is the energy available to do work. And it is the numerical value represented by delta H minus T delta S. So that means that delta G equals delta H minus T delta S. This is the fundamental equation that this whole chapter rests on. Now the idea is if delta G is a negative number, meaning that this is less than 0, then the reaction is going to be spontaneous. If the delta G, the Gibbs free energy, is positive, then it's a non-spontaneous reaction. So let's put over here, negative spontaneous. Actually, let me put it over by the delta G side. If it's positive, non-spontaneous. Ooh, let me duck out of the way there. All right, well, this is what this whole chapter revolves around. They're going to make you do a little legwork so that you have to figure out the delta H of a reaction either by calorimetry or Hess's law or summation of heats of formation. They'll give you some busy work to do to figure out the delta H. They'll also give you a way to figure out the delta S of the reaction. They'll tell you the temperature it's at, and then they'll ask you, is it going to be spontaneous? Well, now be very careful about units here, because generally they give the delta G's in kilojoules. But if you recall from a previous example, the delta S's are usually given in joules per K. So be careful. These are given in kilojoules. If this is in joules, you're going to have to change that one so that they'll match. So again, that's probably the most common mistake made in doing these types of problems. But of all the equations in this chapter, that's what everything hinges on. All right, well, there's one last little topic about delta S and spontaneity we need to look at before we change our focus then to the Gibbs free energy and reaction spontaneity. Okay, so a subtle point here. I mentioned that for any spontaneous process that the delta S had to be greater than delta H over T. But it turns out for an equilibrium process, for instance, like a phase change, like the melting of water from H2O as a solid into H2O as a liquid. Suppose that it was at equilibrium. Well, it turns out that in an equilibrium system like that, remember we said that delta S was actually equal to the physical randomness in the change in the system plus the delta H over T. Well, in this case, when everything's at balance, there's no physical randomness actually being produced because everything's kind of at a steady state equilibrium. In that case, then, the delta S actually equals the delta H over T. I want to show you something kind of interesting here. For water, and this is one of those recall moments, back in Chem 130, we defined the heat required to melt something at its melting point. We called that its heat of fusion. Well, for water, the heat of fusion, in order to melt it, was 6.01 kilojoules per mole. So that means you had to put in 6.01 if you wanted to melt it, or it gave back 6.01 if it froze. All right, well, going forward, if we looked at that positive 6.01 kilojoules per mole, that's the delta H for this equilibrium system to go forward. And it's happening at 0 degrees centigrade because that's the melting point of water. Well, what if I plug that in here for delta S? I put in, now I'm going to do this in joules instead, so that'd be 6,010 joules per mole. And this would be at 273 Kelvin. Well, this turns out to be 22 joules per K per mole. Well, remember I put up the absolute entropies of water as a liquid was 63, and the absolute entropy of water as a solid was 41, or I'm sorry, 41, for a net change of, sure enough, 22 joules per K. So in a roundabout way, it kind of jives that if we know the delta H of a phase change like this, then we can figure out the entropy difference on both sides of that fence. All right, just another example of this phase change equilibrium. If liquid carbon tetrachloride has a standard entropy of 216 joules per K, that's this stuff. 216 joules per K at 25 degrees. Now it's got a heat of vaporization. That's the heat required to boil a mole of it at its boiling point. It has a heat of vaporization of 39.4 kilojoules per mole. So their question is, well, what's the entropy of this stuff then? Remember with the water it was 63 and 41. Well, I'm giving you the starting amount for the CCl4. I want to know what's the ending amount here, that entropy for this stuff. Well, I can find the change in entropy easily enough. The change in entropy is going to be this divided by the temperature we're at, which is 25 degrees. So let me make a little room here. Remember, this was 216. So now what we want is the change in entropy, and the change in entropy is going to be this, but I'm going to convert it into joules. 39,400 joules per mole. I'm going to divide it by the 298K. Well, this turns out to be, hold on just a second. I lost the book. Okay, this turns out to be 132 joules per mole K. Now remember that this is how much it changed. It started off at 216. So actually the entropy here is going to be the 216 plus the 132 for a grand total of 348 joules per K. So there's our answer for the gaseous CCl4. And that reflects the 132 joules per K change in entropy. Okay, just to tie a couple things together here, we've now derived this equation for Gibbs free energy that shows reaction spontaneity if delta G goes negative, and against the difference between the heat hill and the entropy hill. And we also looked at the change in entropy then for a phase change. For instance, water going from solid to liquid. We mentioned earlier that the delta S here was 22 joules per K because this started off at 41 and this went to 63. And so it was easy to calculate from standard absolute entropies what the change in entropy here was. But I showed you that we could also do it by the fact that delta S for any equilibrium system is delta H over T. Well, the delta H, the heat of fusion for melting water, is a positive 6,010 joules per mole. If it freezes, it gives up that 6,010. All right, well, if we divided that 6,010 by the temperature that we're at, it came out to be 22 joules per K. All right, well, I want to plug that into our expression for Gibbs free energy and calculate what would the Gibbs free energy be for this reaction at equilibrium. Well, at equilibrium, this is 6,010 joules, right, to go forward, minus 273 times 6,010 over 273. That's how we calculated delta S. Well, notice this is going to come out to be 0. These cancel out. 6,010 minus 6,010. There's no change in Gibbs free energy when this is at equilibrium. But what if I wanted to force the reaction to go forward a little bit? What if I just warmed up the ice a little bit? Wouldn't the reaction start to melt, start to go forward? And sure enough, if I were to raise this temperature, remember this delta S has to be the normal freezing point for the water. So if I jack the temperature up, suddenly this flips to negative and the reaction becomes slightly spontaneous. All right, well, let's look then a little closer at the relationship between delta G and the temperature of the reaction. How can we adjust the temperature to bring about spontaneity? Okay, reaction spontaneity, delta G, and temperature change. All right, well, I've talked now about this heat hill and randomness hill, and they're kind of competing factors in whether or not a reaction may go spontaneously. But I think everybody would agree that if a reaction is rolling down the heat hill, which is favorable, spontaneous-wise, and it's also rolling down the randomness hill, meaning everything is favorable, it's got everything going for it, then there's no way that this reaction cannot go spontaneously. So if we look just at the equation, that if the delta H was negative, meaning the reaction was exothermic, is rolling down the heat hill, that's favorable. The delta S being positive, that's more random. That's favorable. Well, delta G has to be delta H minus T delta S. Now remember, T is in Kelvin, so it cannot be a negative number. It's going to have to be positive. So if the delta H is negative and the delta S is positive, then there's no way that delta G can be anything but a negative value. You see what I'm getting at? Both things rolling downhill, both of them are favorable, both driving the reaction forward. Delta G most definitely will come out negative, which is an indicator of reaction spontaneity. All right, well, what if it had everything going against it? I mean, what if it was an endothermic reaction where the delta H was positive? And suppose it was trying to get more orderly, where the delta S was negative. So it's rolling up the heat hill, up the randomness hill. There's no way this thing is going to come out of the gate by itself. You're going to have to kick it out, and you're going to have to push it the whole time. So the delta G is always going to be positive. And it doesn't matter what the temperature would be, because in delta G, let me put that equation up here at the top so we can refer to it. Delta G being equal to delta H minus T delta S, it doesn't matter what that temperature is, because in this case, if the delta H is positive and this is negative, well, then most definitely, even if we were close to absolute zero, the delta H would still be unfavorable and make the delta G unfavorable. The reaction just will not go spontaneously. Well, then you can see where this is headed. What if there's a trade-off? What if one of them is favorable and the other one is unfavorable? So suppose the delta H was positive, but the delta S was positive also. Well, let's look at the equation again. Delta H minus T delta S. I shouldn't have erased that. Suppose the delta H is positive, but the delta S is positive. Now look closely at this equation. We want delta G to be negative for a spontaneous reaction, but it's fighting this. The delta H is doing something unfavorable. It's rolling up the heat hill. So we need to make sure that this term is very large because we're subtracting it. We want to subtract a significant amount so that we could negate all of that delta H and go to the negative side. Well, that implies that the temperature is going to have to be really big, because if this delta S is, even a reasonable number, we're still going to have to drive the temperature up. It's more likely to be spontaneous at a higher temperature than at a lower temperature is what I'm getting at. So when you look at a reaction where sure enough you've got one thing favorable and one thing unfavorable, you're going to have to decide, well, which way is the temperature going to give me what I want? Do I want to jack the temperature up or reduce it? Well, in this particular case, the delta G would be negative at high temperatures. On the other hand, what if the delta H was the favorable part? What if it was the driving force of the reaction and the delta S was negative? It was trying to get more orderly. Well, if the delta H is negative, that's good. I mean, we want that. That's favorable. If this is also negative, then subtracting that negative is not helping. That's chipping away at this driving force of my reaction. So in that case, I want to minimize this entropy term because it's the one that's going uphill. This is the one that's going downhill. So let's make this as small as possible, or uphill. So that means drag that temperature down. Chances are a reaction like this, that's exothermic and is trying to create orderliness, is more likely to run at lower temperatures and be spontaneous than at higher temperatures. So delta G would be negative at low temperatures. Now that kind of flies in the face of logic. You think, boy, reactions usually go faster when you heat them up, but there are a small handful where you've got an exothermic reaction creating orderliness that run much better at lower temperatures than at higher temperatures. Okay, well, let's look at a problem that involves this. All right, so let's take a look at a problem that kind of reflects this idea of situations where changing the temperature might cause reaction spontaneity. For example, calcium carbonate. This is the main component in just regular old chalk. It turns out that under right conditions, it can decompose into calcium oxide, a solid, and carbon dioxide gas. Well, this is a nice fine powder, so chalk would eventually become this fine powder and CO2 would escape. Well, I don't think that reaction is very spontaneous at room temperature because I've left pieces of chalk laying in the chalk trough for weeks, and they don't seem to evaporate. So apparently this reaction does not favor the product side and definitely does not go spontaneously. You'll notice that I summed up the delta H of formations for the products and subtracted the reactants and found the delta H of this reaction is endothermic, positive 178.3 kilojoules. So that's kind of an uphill battle. You can understand that heat-wise, it's going up the hill. All right, well, the entropy, and if you look at this, you could kind of predict that it would have a positive change in S because there are two molecules on this side of the equation and only one, so it increased the randomness. But in addition, it made a gas, which again adds a lot to the entropy. So it definitely would have a positive delta S, and it turned out, yeah, if I sum up the absolute entropies of calcium oxide and CO2 and subtract the initial entropy of the calcium carbonate, it came out to be a positive 159 joules per K. All right, well, that's a favorable thing, creating randomness. So the question is, the heat hill that's going up, the randomness hill that's going down, apparently the randomness hill is not enough downhill to pay for that uphill battle because the chalk, again, does not spontaneously decompose. Well, let's plug these numbers into our check for spontaneity. Let's calculate the Gibbs free energy for this reaction. All right, so the delta G at 25 degrees centigrade would be the positive 178.3 kilojoules that we got for the delta H. We're doing this at 25 degrees centigrade, so that's 298 K. And we'll multiply that times the change in entropy. Now be careful here. I gave that entropy change in joules per K, but we need it in kilojoules. It was 159, so I'm going to make it a 0.159 kilojoules per K. Well, this turns out to be positive 130 kilojoules when you calculate the delta G at 25 degrees centigrade. Well, it's clearly not spontaneous, and that's kind of an uphill battle. So this is what was keeping it from going, was the endothermicity of it, how positive a hill that was for the heat. There wasn't enough entropy actually created here, at least at this temperature, in order to overwhelm that unfavorability of it being endothermic. And consequently, the reaction at 25 degrees does not go spontaneously. However, entropy does go where the heat goes, and we mentioned that reactions that have a positive delta H and a positive delta S might happen better at higher temperatures. So what if we were to take this chalk, toss it in a furnace, say at 1,000 degrees centigrade? All right, well, let's plug in 1,000 for our temperature. As a matter of fact, the only thing that would change here would be this. Instead of 25 degrees centigrade, let's say we popped it in the muffle furnace. That's something we always like to play with out at daily labs. They had a muffle furnace. You could crank it up to 1,500 degrees centigrade, throw pieces of paper in there, and they would just vanish. It was woof. So anyway, 1,000 degrees centigrade. We throw a piece of chalk in there. All right, well, that's 1,273 Kelvin. And sure enough, it changes the delta G value to a negative value, the fact that this temperature is so high. And it comes out negative 20.4, I believe. Let me double check my numbers. No, negative 24.1, just in case anybody's out there checking. The key thing here, though, is that it's negative. Sure enough, at 1,000 degrees centigrade, this chalk will begin to decompose into calcium oxide and CO2. Again, because the delta G is now favorable at this higher temperature. All right, well, that kind of begs the question then, at what point did it actually flip? I mean, we know that it wasn't spontaneous at 25 degrees, but it was at 1,000 degrees. So somewhere in between there, it began to decompose. Could we find the minimum temperature at which that decomposition started? Well, let me erase this and show you it's pretty easy. Because if we want to know where delta G flipped from positive to negative, we essentially want to know at what temperature then did this equal zero? Right at the point when it flipped from positive to negative. So if we plug in the delta H we know and the delta S we know and leave delta G to be zero, we could solve for the temperature minimum. As a matter of fact, the temperature minimum for this reaction would be the delta H divided by the delta S. Well, if we divide the 178.3 kilojoules here and divide it by the 0.159 kilojoules per K for delta S, we end up with, 1121 Kelvin. Well, that turns out to be 848 degrees centigrade. Well, that's not unreasonable. We know it wasn't spontaneous at 25, but it was at 1,000. Well, it turns out that right at 848 was when it flipped to a negative delta G. That would be the minimum temperature required then to make this reaction go spontaneously. All right, well, this seems like a perfect spot to stop and kind of summarize and review what we've just looked at before we do our second module on thermo. Okay, we actually covered quite a bit of the chapter on thermo. There's not a whole lot left to it. So I'm going to do another module and then kind of review everything that we did in the thermodynamics and do kind of a quick review for the exam. But you can pretty much figure once we wrap up this thermodynamics business, it's time to figure out how we're going to do a test. Well, all the material that we covered in this first module actually helps with the homework all the way up to number 65. I think that only leaves maybe 3 other homework problems that will be discussed in the next module. So anyway, once you've watched this, sit down and try those problems up through number 65 that I assigned in chapter 19. Now, again, just to kind of summarize what we've talked about, we talked about delta H, and I gave you a little bit more theoretical background here than we really needed. I talked about delta U just so that I could explain to you that delta H is the heat of a reaction measured in an open container, meaning it's the heat at constant pressure. We looked at 3 ways to measure it. Calorimetry, we looked at the summation of heats of formation. I'll just put summation. And we looked at Hess's law. Now again, these are all review topics from back in chapter 6. They're not covered in detail in chapter 19 again. You could go back and look at it, but again, I'm going to give you a lab that sort of illustrates all 3 of those. And we also looked then at delta S, since it's these 2 that determine the driving force behind a reaction. It's a trade-off between these 2 to ultimately decide reaction spontaneity. And again, there's really only one way to find the change in entropy for a reaction, and that's the summation law. The summation of standard free entropies. And again, the appendix of your book has the standard free entropies and the heats of formation for all of the compounds that you'll need. I think it's appendix 2. So if you're doing problems where they have you calculate a delta H or a delta S, this is what they want. Go to the appendix, look up the values, do the arithmetic. It's real easy to drop a negative sign in there, so be very careful when you're doing the summations. Now, once we did this and we calculated the delta H and the delta S, we kind of introduced the second law then when I was talking about the delta S, that the entropy of the universe is always on the increase. That regardless of any process, if you sum up the entropy of the system, even if it got more orderly, and add to that the entropy created in the surroundings, the net change is always going to be a positive value for any kind of process, whether spontaneous or not. Let me find an eraser here. Now, once we had talked about delta H and delta S in detail, then we wanted to talk about reaction spontaneity. We said for any spontaneous process that delta S had to be greater than delta H over T. All right, and I kind of gave you a little theoretical background on why that had to be true. And so we also pointed out, though, for a system at equilibrium, for instance, like a phase change, where you're melting water or you're boiling water, that at that phase change point, the delta S is actually equal to the delta H over T. That's because at that equilibrium point, there's no net change in the physical entropy that's being created in an equilibrium system. And so consequently, delta S equals delta H over T. But this was the one that really led us to the equation. We rearranged this and just said, well then, delta H minus T delta S has to be less than 0, has to be a negative value. But we gave a name to that value. We called it the Gibbs free energy. And delta G was equal to delta H minus T delta S. For spontaneity, this has to be less than 0. That simply means delta G has to be a negative value. The more negative it is, the more likely reaction spontaneity is going to occur. All right, so again, they had you calculate delta H's and delta S's ultimately so that we could get to this delta G. Now, in addition, there's a way to measure delta G's without going through the process of finding the delta H and the delta S. In your appendix, they also list the standard Gibbs free energy of formation for all the compounds. So you can find the delta G of a reaction by simply doing a summation of the Gibbs free energy of formation for the products minus the Gibbs free energy of formation for the reactants. So, nice little shortcut there since they list all of them for you. If your ultimate goal is not to find delta H or delta S, but just to find delta G, this is definitely a quicker way to do it and will indicate whether you're going to look at a spontaneous reaction or not. And so let's see, second law, what else did we look at? Oh, the fact that delta G, and I just mentioned this very briefly as we were discussing it, but for a system at equilibrium, the delta G at that point is equal to 0. It turns out if a reaction is, let's say, on one side of an equilibrium, let's say it hasn't reached equilibrium yet, it's still trying to go forward, it would be spontaneous going forward, and the delta G in this case would be negative. But if the U-shaped tube was the other way around, suppose we had too much product to be at equilibrium, and the equilibrium wanted to shift this way, well then the delta G in reverse would be a negative value. It'd be spontaneous to go backwards, here it would be spontaneous to go forward. But at the point where it reaches equilibrium, where it's at a steady state, at that point, there's no net change in the Gibbs free energy and the delta G would be 0. We're going to use this fact in our second module to show a couple other interesting things, like the connection between the equilibrium constant of a reaction and its actual value of its delta G. All right, so these first few problems are more arithmetic problems than anything else. But the key thing to remember is that reaction spontaneity, that concept. Negative delta G, spontaneous. Positive delta G, non-spontaneous. Okay, well, I'll see you in the next module. We're going to discuss, like I said, a little bit more about equilibrium and spontaneity. And if you have any questions, again, don't hesitate. Just email me or text me, and I'll get right back to you. Now, I'm still trying to work up a live meeting with everybody. It looks as if we might be able to use Google Meet since now they've incorporated it in everybody's student email accounts. So let me do a little experiment with it, and we'll figure out a way that we can actually get together and do a quick Q&A live. Actually, it doesn't have to be quick. But anyway, I'll see you in Module 2.